Hello friends, welcome to this video about Booth's algorithm implementation in binary multiplication. The objective of this video is to explain how to implement the Booth's algorithm for multiplication of binary numbers. In the previous video, we explained the concept of Booth's algorithm as an introduction to the present video dedicated to the practical implementation of the Booth's algorithm approach in binary multiplication. If you haven't seen the previous video about the concept, I recommend you to check it first. The Booth's algorithm method operates by examining consecutive pairs of bits in the multiplier and performing arithmetic operations based on these pairs. After a series of iterations, the method finally generates the product result. First, we have to highlight that the method works with signed numbers. The most advantage of the Booth's algorithm method is obtained when the multiplier has a sequence of consecutive ones or zeros in the number. For example, here, where the number contains a series of consecutive ones. In the process, the algorithm checks two bits, q0 and q-1, during each iteration, and based on these two bits, either add, subtract, or only a shift operation is performed. The method uses 2's complement representation of numbers to handle both positive and negative values, so to convert subtractions into additions. This process is repeated until all the bits of the multiplier are checked. So, in this video through examples, we will understand how this Booth algorithm works and how, using it, we can reduce the execution time, making it faster and hardware efficient compared with the previous methods. Let's compare the Booth's algorithm method with the partial sum approach method. In the Booth's algorithm method, instead of comparing a single bit, it compares two bits at a time. The Booth's algorithm method uses arithmetic right-shift operation, whereas the partial sum approach method uses logic right-shift. In a previous video, I have explained the difference between logic shift and arithmetic shift, so in case you need, you can check it. The partial sum approach method, in its basic form, only handles unsigned numbers. While the partial sum approach could be adapted for signed numbers, the Booth's multiplication algorithm is often preferred because it efficiently handles 2's complement numbers and reduces the number of partial sums. To implement this method, the following registers are used: multiplicand, multiplier, and accumulator. The accumulator register is the temporary storage where the successive partial products are accumulated and combined to form the final product. These registers are similar to those used in the partial sum approach method. But in addition, we need to use another register, the register q-1. This register is the right shift of q0. During the process, we arrange these registers in the following form. Initially, the content of the accumulator register is clear to 0. Clear to 0. Also, the register Q-1 is initially set to 0. So initially we have this configuration. As you see, the multiplier register and the accumulator register together conform the 8 bits needed for the product result. During the process, the value of these registers change according to the steps of the operation. And at the end of the process, the combination of the actual values of the registers A and Q show the final product of the multiplication. The final product of the multiplication. So, as I said, initially we have the following configuration. The content of the accumulator register is clear to 0. Also, the register Q-1 is initially set to 0. Then we will start, and on each step of the process we compare these two bits Q0 and Q-1, and according to this comparison we apply this table. Let's explain the content of the table. If this Q0 and Q-1 are 0 and 1, we perform this addition and the result is stored in the accumulator register. If Q0 and Q-1 are 1 and 0, we perform this subtraction and the result is stored in the accumulator register. And if Q0 and Q-1 are 0, 0 or 1, 1, we only perform a right shift operation. So, based on the comparison of these two bits, we perform either an addition and a right shift, a subtraction and a right shift, or only a right shift operation. So note that after each addition or subtraction, the result will be stored in the accumulator register. Note also that afterwards, in both cases, we will perform a right shift operation. If Q0 and Q-1 are 0, 0 or 1, 1, then no addition or subtraction will be performed. In that case, we'll go directly to perform the right shift operation. Remember that in binary, a subtraction is equivalent to adding the 2's complement. And the process will be finished when we have completed n shifts, where n is the number of bits. Let's see an example of multiplication of m times q, where the multiplicand is 1110, which is equivalent to -2 in decimal, and the multiplier is 0110, which is equivalent to 6 in decimal. Let's start. This is the accumulator, this is the multiplier, and this is the Q-1 register. Initially, A and Q-1 are set to 0. In the first step, we compare Q0 and Q-1, and it is 0, 0, so we have to do a right shift only. So this is the right shift. Then, in the second step, we compare Q0 and Q-1, which is 1, 0. That means that we have to do a subtraction and a right shift. Because it is a subtraction, we add the 2's complement. This is the 2's complement of m. This is the 2's complement of m. We add it with A and we have 0, 0, 1, 0. So we have performed A plus the 2's complement of M. Now we have to do the right shift, and here we are doing the right shift. Then we perform the third step, and we compare Q0 and Q minus 1. And because it is 1, 1, that means we need to do a right shift only. So here we have done a right shift only. Then we do the fourth step, and we compare Q0 and Q minus 1. And because it is 0, 1, that means that we have to perform an addition and a right shift. An addition and a right shift. So here we add the multiplier and we obtain A plus M. And now we have yet to do the right shift. So here we perform the right shift. We perform the right shift arithmetic to maintain the sign of the bit. Remember that the multiplication result is given by the combination of the register bits of A and Q together. Let's verify if the result is correct. It is minus 12. It is minus 12. So it is correct. So this is the result of the multiplication. Because we are working with 4 bits, the result is made with 8 bits. And the process is finished when we completed the 4 bits, where 4 is the number of bits. First shift, second shift, third shift, fourth shift. Remember that this shift is this shift, and this shift is this shift. So in total we have made 4 shifts. Remember that in this example we have performed 4 shifts, but only 2 additions. 1 addition, 2 additions. So the advantage of this method is that whenever there is a series of 1's in the multiplier, here we have a series of 2 consecutive 1's in the multiplier, then there is no need to perform the arithmetic operation, and in this way we can reduce the required time for the multiplication. Now, this is the flow diagram of the Booth implementation process. This is the accumulator initially set to 0. This is the Q-1 register initially set to 0. This is the countdown from the number of bits. And this is the multiplication. This is the comparison step of Q0 and Q-1. When there is 0, 1, we do the addition operation. And when it is 1, 0, we do the subtraction operation. This is the arithmetic right shift. And this is the countdown from the number of bits to 0. When there is no 0, we look back and we repeat the process. And when we reach 0, we stop. I will not go into details. It is quite self-explanatory. I let you to go through by yourself. And this is the flow diagram converted into a hardware circuit. Let's explain it. This is the accumulator and this is the multiplier. This is the bit Q0 and this is the bit Q-1. Depending on the value of the pair of bits Q0 and Q-1, the control unit makes directly the right shift or first activates the multiplexer. The multiplexer, depending on the control unit, if the pair of bits are 0, 1 or 1, 0, selects either the multiplicand or the 2's complement of the multiplicand. Then the other adds the output of the multiplexer to the value of the accumulator and stores it into the accumulator. And finally, the final result is given by the combination of the register A and Q bits together. A and Q bits together. So now we are ready for the conclusions. In summary, the boost decoding algorithm can efficiently reduce the number of additions during the multiplication. The number of additions depends on the number of ones in the multiplier. During the process, the algorithm checks 2 bits Q0 and Q-1 during each iteration, and based on these 2 bits, either performs an addition, a subtraction, or only a right shift operation. The most advantage is obtained when the multiplier has a sequence of ones in between, with some leading and succeeding zeros. Compared to the partial sum approach method, the number of shifts in the boost decoding algorithm is similar. However, the number of additions gets actually reduced. Also, in this session, the flow diagram and the circuit block diagram for the boost multiplication have been presented. That's all for today. Thank you very much for your attention. Have a nice day. If you like this video, please hit the like button and subscribe for more videos. This video completes the series of videos dedicated to binary multiplication. In the next videos, we will explore how to perform binary division.